Well, in the previous slides, we have shown that we are able to monitor the temperature using MR. But MR monitoring of HIFU is not only restricted to thermometry. You can also use other methods to encode information in the MR signals. For example, the push that is induced by a short ultrasound burst. This is called Acoustic Radiation Force Impulse Imaging, or ARFI, MR-ARFI. And for example, you can use different kind of sequences, a spin echo sequence that is displayed here. And from this standard sequence that is available on any scanner, you can add, for example, a pair of gradients, bipolar gradients, and you can synchronize the emission of the HIFU pulse with one lobe of the gradients. And you can, for example, repeat this within a sequence to increase the sensitivity of the method. For the tissue that are not submitted to ultrasound pulse, the phase of the MR signal accumulated during this lobe is fully compensated by this one, and that's the same for this second bipolar gradient. On the contrary, for the tissue that are exposed to HIFU, the phase accumulated during this gradient is not compensated from this gradient, and that's the same for this second lobe here. In other words, using this technique, you encode into the phase of the signal not the temperature, but the displacement. Okay? If you're using this, you can, for example, create a displacement image here on the right, and you can plot the displacement value as a function of the acoustic power you're sending. So if you stay below a given power, you remain in a linear regime, and then you can clearly see that your displacement is proportional to the acoustic power. However, if you send very strong bursts of HIFU pulse, then you can go outside from this linear regime. For example, if you make cavitation, or if you're making shock waves, or if you're doing boiling. Okay? So this can be exploited to increase the heating efficiency of your MR-HIFU system. How? Well, imagine we make a simple experiment. We first make a measurement of displacement without strong energy. Then we make at the same locations a standard HIFU sonications with moderate power, 20 watts during 30 seconds. You get an elongated shape of temperature distribution, which is really classical with the HIFU system that are used clinically. I mean, for the abdomen, for example. Now, if you modify the tissue characteristic, for example, by using a HIFU pulse, quite intense and short in duration. Well, short depends on the acoustic phenomenon you want to exploit. Here it was 500 watts for 200 milliseconds. And then you repeat exactly the same experiment. You measure the displacement you can create with moderate push intensity. Then clearly you see that you have a strong change in your displacement map. And then if you repeat exactly the same heating protocol with the same power and duration, you can clearly see from the image in the bottom right that you have a much stronger temperature increase and a much larger spread of temperature. Okay? So this has been demonstrated both ex vivo and in vivo in a large animal model. And these are the temperature curves you can retrieve on the liver with a standard sonication and with the same sonication with the same energy deposition, but after modifying the tissue characteristic by adding a strong and short duration pulse, HIFU pulse. And you can see on the images on the top right that the lesion is completely different. You can only achieve something which is more close to the hemorrhage, to really a clear ablated region for about 1 centimeter in diameter. And these two lesions were created with exactly the same energy deposition from the acoustic point of view. And simply by using MR-HIFU, you can tune the parameters and adjust the acoustic intensity to create this nonlinear effect. For example, here it was boiling, to increase the size of the lesion while avoiding overheating of the near field, because then you stay for the ablation itself in a quite moderate energy deposition. So what I've shown you before is that we are able with MR to encode the temperature into the phase of the signal. But we are also able to encode also into the phase displacement. So from the displacements, is by using a pair of gradients and synchronizing a pulse with one of the lobe of the gradients. And for thermometry, is simply the phase change that is related to the PRFS technique. Well, it's possible to combine both of them and to get in a single measurement both the temperature and displacement. How can we do that? This is an example using, again, EPI for fast acquisition method, where we can include a pair of bipolar gradients for measuring displacement. And if you change the polarity of this gradient as a function of time, you alternate them for odd and even acquisitions, then you can make the sum or the difference of the phase that images that are related to temperature and displacement. Then you get, for example, a bright signal in the sum and a dark signal in the difference. And this alternates as a function of time. And if you do that simply by making a processing of phase and difference in successive images, then you can retrieve from the same measurements the temperature distribution and the displacement. And this can be, for example, interesting to monitor at the same time the change in displacement and the change in temperature. So this is an example of results obtained in vivo in a liver of pig, where you have the temperature and the displacement before, at the beginning of the treatment, and at the end of the treatment. And what you see from the curves that are displayed on the right, that the temperature increases enough to create an ablation, and you can clearly see that the displacement reduces in value as a function of time. So using this, you can have a second metric in addition to temperature and accumulated thermal draws, which is the displacement at the focus. C'est bon? OK. 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 Alors là, j'ai ça, j'ai ça. So as I mentioned at the beginning of this talk, it's also possible to use this real-time monitoring not only for measuring what's happening in real time, but also for controlling the HIFU energy deposition. For example, you can predefine a temperature versus time profile that you would like to achieve and let the system adjust dynamically the acoustic intensity depending on the temperature map that you're collecting at each time point. For example, here you have an overheating. Next time you have to slow down the energy deposition. And then if the next point is much below, then you have to increase the energy deposition. Then you can use a lot of methods that are already known for automatic control, not specifically to MR or to HIFU. These are really well-established engineering methods that you can exploit here to adjust dynamically the acoustic power deposition to force the temperature to follow a predefined target. This can be particularly interesting for non-destructive application of MR-guided HIFU, for example, for local drug delivery or activation of a gene. And this is really an active area of research. Other methods for MR-HIFU include monitoring of several parameters simultaneously. I've shown you before an example of simultaneous measurement of temperature and displacement, but there are new methods that have been recently published where you can, for example, monitor the relaxation time, the T2 in fat, because as I said before, the PRFS does not work in fat. However, it has been shown that the T2 increases with temperature in fatty tissues. And for example, this can be very useful for checking if the temperature increase in the near field on the skin, for example, or in the subcutaneous fat, does not exceed a given value. For example, when you're doing consecutive heating to treat various regions of a large volume. Other methods include simultaneous monitoring of T1 and PRFS. For example, if you want to monitor the local drug delivery, if you have drugs encapsulated into nanovehicles simultaneously with MR contrast agent that affect the T1. So you can use these techniques in real time to monitor two parameters. As a conclusion, MR-HIFU, covering MR-HIFU, MR-guided HIFU is very difficult because you can have a large number of methods, either for planning, monitoring, and following up. And what's important is that each time you want to develop a new method, either for concepts on some small animals, in translational research if you want to test preclinical methods on organs that have similar size as those from humans, or if you want to test or evaluate your methods on patients, you need to think not only in terms of HIFU hardware, you also need to think about hardware from MR, acquisition methods, what are the spatial and temporal resolution, what is precision do I need. It's not the same if I want to do ablation or if I want to control a small or moderate temperature increase of 5 degrees above the body temperature to monitor drug delivery. Does not require the same performance. And each time you need, or for each application, you need to have dedicated methods. So I would like to thank you, and I want to conclude by saying that the references that have been included into this presentation are of course not exhaustive, because this field is really very active, and you have a lot of new methods that are continuously be published, either on acquisition, speed, increasing the speed, precision of the construction, including, for example, modeling into the reconstruction to reduce the number of data to acquire to make 3D images. And it was very difficult to cite every group and everybody active in this field. So please forgive me if there are some missing references, and please enjoy into this very exciting field. Thanks.